Hey folks, since we had so much fun with that lead compensator design, I thought I would make a quick video on lag compensation. So what we'll do is have a look at these notes, and I'm not going to step through them bit by bit. We're just going to kind of take a high level look at them and then hop into MATLAB and complete the design for the same example that we did for lead compensation, but this time for lag compensation. Now, lag compensation is arguably a little bit easier than lead compensation. There's less moving parts, so to speak. You can achieve some of the same objectives. You can get steady state error requirements met. You can go after phase margin. The problem is that you typically end up with a little bit of a sluggish response, a little bit of a slower response. If that's okay, then maybe this is the compensator for you. The other thing that happens is because of that sluggish response, you often don't need as much actuation effort to get the job done. But it comes at a price. It's slower. So here is the compensator. It looks very much like a lead compensator. We've got a 0, so TS plus 1, and the denominator a beta times TS plus 1. It's a very similar looking form, except here beta has to be greater than 1. And so what that's going to do is create a pole close to the imaginary axis and a 0 right near it, typically. The Bode plot for the compensator is right here. And you'll notice a couple things. First off, we lose phase with a phase lead or phase lag compensator, and that would seem like a bad thing, and it could be if you design the compensator incorrectly. The interesting part is that instead of a magnitude gain that we had for the lead compensator, we actually now have a gain attenuation, especially at high frequency. So it starts out at 1 or 0 dB, then it ramps down and then ends up at some level down here. And that decrease in gain can help you a lot, because what it does is it can shift the gain crossover frequency of the plant to the left. The only thing you have to do is make sure that this nasty phase bubble, which is negative, is far away from the high frequency magnitude attenuation or gain attenuation that you're exploiting over here. Now, like with lead compensation, there were a couple, little details that we had to keep track of. One was the gain amplification that we had to adjust for, and the other was the fact that we didn't quite get all the phase that we wanted to because the phase was tapering off a bit. Well, there's just one of those things we have to worry about here, and that is this phase bubble. It kind of has this tail on it, and that little tail is going to eat into us for a couple of degrees, 2, 3, 4, 5 degrees or so of phase margin. So once you figure out how much phase margin you need, from a minimum standpoint, you do the same sort of trick. You just say, I'm going to ask for another 10% or so. And that's how the design works. Now, the design formulas are shown here, and they really just make sure that those things happen. That is, this one makes sure that I get the high frequency gain attenuation that I need. And this one makes sure that the phase bubble is far to the left. Now, this is just a way of doing it, 10 over the desired gain crossover frequency, but you could make this a different number, or you could make this 20, and that will help you a little bit. You won't have as much of this little tail of the phase loss to deal with. You'll be operating more over here. If you increase the numerator even further, you'll operate over here. Now, the way I drew this, it looks like the negative phase bubble goes to 0, but it doesn't. So no matter what you do with this numerator, you'll still have to ask for just a little bit more phase. But if you increase the numerator, you won't have to ask for maybe 10% more phase, maybe just a couple percent. And that's actually probably the best way to go, is to maybe use 20, 30, 40 up here in the numerator and only ask for a few percent extra phase. That'll typically give you a little bit better design. So that's it. I didn't really describe the design procedure in detail, but you'll see that as we go through this example. Same example that we had before. Got this little plant here, pretty harmless little plant. And we want a steady state error of 0.005. So that means that the K of our phase lag compensator needs to be 200. So I'm going to take that 200, stick it into the plant, and then just move on to calculating beta and capital T. So well, actually, let me show you how that works here, and then we'll do it in detail in MATLAB in a second. Oh, there's Chloe. Well, maybe she'll come in and pay us a visit. So what you do is you look at the Bode plot of the plant, the gain compensated plant, that is with the 200 in it in this case, and you just figure out where you want to be in terms of phase margin. So for example, and actually I need to pick up this cat, because if I don't, she's going to talk to us, and that'll be kind of tricky. So there we go. So you may hear some purring, but that's okay. So here's what I mean by that. Here's the Bode plot of the gain compensated plant here in blue. And we want 50 degrees of phase. Now I have a 55 degree phase line here. That's with the extra 10%. But let's just pretend like we're going to go for 50 degrees of phase margin. So all you have to do is look at this magnitude plot and say, how much do I need to knock off? How much do I need to move it down until I get 50 degrees of phase margin? So that would be, let's see, that'd be about 100. What would that be? 50, 130, I guess. So this is probably 125. So 130 is probably right here. So I would need to move the magnitude plot down to, maybe this much. And that's it. That's really, what we have to do to find, to find M. And then we just, and that's in dB, and so then we have to convert that to beta, which is in, not dB. So we have to do the inversion of that. We'll do that in MATLAB. So, we've got half of the design done. We actually have the whole design done at that point, because, once we know what this, once we move this down, that decides for us the gain crossover frequency. And once we have that, going back up to our formulas, we have this. Boop. So we're good. So let's do it. And I think we're about done with this. Yeah, I mean, you can go through some of the details here, but yeah, we won't spend too much more time with that. So let's move into MATLAB. And I guess we'll start the same old way we always start. Make a transfer function of the plant. So what do you think of that, Chloe? She's trying to keep me from typing. I think that's about right. Yeah, looks about good. And let's see, I'll go figure 1. We'll do go margin G. So we'll kind of go through this process again a little bit. Excuse me. And let's throw a grid on that. So we'll go through the same process we just did by looking at the pre-manufactured plot. Okay, so let's see. All we have to do is figure out how much we want to move this magnitude plot down to get 50 degrees of phase margin. So, 180 minus 50. So we need to get to 130, negative 130 basically. So maybe I'll put a dot there. Negative 103. Where's negative 130? Oh, there it is. So we're at about 2.09. So I'm just going to, I was going to jot that down, but I guess I could jot it down right here. So we're going to say omega, the one that we want from the design, is at 2.09 radians per second. And we now have half the design done, right? We could solve for capital T without too much trouble. We could just do that now. We could say T is equal to 10 divided by that omega, I think I called it omega GD in the slide. And there we go. All right, now let's figure out what M is. So that's 2.09. So I'm going to come up to here and get to 2.09. Oops, almost had it. Oh, come on, that's close enough. So the magnitude is 37.2. So that is M. So 37.2 dB, and if we want beta, that would be 10 to the M divided by 20. All right, so I'm taking the 37.2 and converting it back to a regular old decimal value gain. And we come up with 72.44. You know what? I think we're done with the compensator at this point. So I'll call this D1. And D1 is a transfer function, and it is the T1, boom, beta times T1, boom, like so. Look at that. Well, let's see what happens. Now, keep in mind, this is the wrong way to do it, because I didn't ask for quite enough phase. This was, theoretically, 50 degrees is what we wanted to meet the design of phase margin 50 degrees. But the problem is that our little phase bubble is going to eat away just a little bit of the phase. So we're going to see that in a minute. So let's make a new plot. We'll use Bode, and we'll plot about G, and G times D1, and how about D1? That way we'll see the compensator also. Whoa, there's a lot going on there. Make that a little bigger. There we go. Oh, you know what? It'd be nice to have a grid on that. Okay. How cool is that? So here is the negative phase bubble. I was calling it a nasty negative phase bubble. And it is far to the left of our gain crossover frequency, which is here. But it's not quite far enough to the left, because look what happens right there. That little piece of phase is going to eat away at our 50 degrees of phase and sort of corrupt the design a bit. Now I could click on this and pick off points and stuff, but instead I'll just throw up a margin plot of G times D1. But before we do that, you can see in blue the original plant transfer function. And what this phase lag compensator did was it dipped the phase down back here, which could be catastrophic if the gain crossover frequency was really low back in here. But it really doesn't hurt us at all in the area that we're interested in, which is over here. And so what we're doing is hoping that the compensated frequency response in the phase plot sort of hugs the original plant from about here on out. And of course it doesn't. Again, we're eating away at some of that phase. I guess from about here on out. Okay, so let's throw let's use the margin command. So I'll go figure 3 margin just G times D1, like so. And here it is. Pretty funky looking, plot, but you can see that our phase margin is only 44.2 degrees. And the reason it isn't 50 is, once again, because of this. And now what I'm going to do is prove to you that this is what caused the problem. So at the gain crossover frequency, which is, it should be really close to about 2.09 or so. There it is. Oh, 2.13. Okay. So 2.13, that's close enough. And if I come down to here at 2.13, oh, I almost had it, really. We lost, ooh, look at that, 5.55 degrees. Now, 44.2 plus 5.6, so that would be 49.8. So this is what caused it. Is this little doofus right there. And if I use eval FR and I got everything just right, I would get just right the you'd see perfectly that this is what caused the degradation of that phase margin. So there you have it. But so now let's do it the right way. Well, actually, there's a couple ways to do it the right way. let's see. Let's do it by first just taking this equation, and instead of doing 10 divided by W, I'm going to do 40 divided by W. And what that's going to do is it's going to push this phase bubble further to the left. And so in the vicinity of the gain crossover frequency, these two lines will line up atop each other much better. But no matter what I do with that, I'm always going to have a wee bit of phase that I lose due to that nasty phase bubble. So we'll see that. So I do that, and I don't have to do anything more with M. So now what I'll do is, well, I'm just recompute D, really. And I'll make this a D2. I guess I call it T there, so voila. So let's go figure 4 and do the margin command on this. And we should get a little bit more phase margin. The original design had 44.2, and now we have 48.4. Now I could make that numerator, 10 here, 40 there, I could make it larger and larger, and I'll never get to 50. I'll get closer and closer, but I'll never quite get to 50. So I have to ask for more phase margin. This is kind of funky looking. So what should we do? How about, we're going to do 2 more designs. Let's redo the design and ask for 55 degrees of phase margin. So 10% of, where we started. And I can actually pull that off of, I can pull it off of this plot, I guess. This is our original plant, and if I want 55, I just have to move this to 125, negative 125. Oh, there we go. So that's 1.76 radians per second, and so there's the W. And now I'm going to move this to 1. So now W is 1.76 and M is 39.4. So I'm going to go W is, where is it? 1.76. Okay. And M is 39.4. 39.4. Okay. And so I'm going to redo beta. All right. Same old formula there. And we are almost done. So now I'm going to redo T, and I'm going to go back to the 10 over W. Okay? And what do we have? I guess we're done. And so now I'll create the compensator. And I think that is good. And now let's make a new Bode plot. And we'll make this figure 5. Boom. It's a colorful thing, isn't it? Put a grid on it. And I'm going to make yet another figure, how about 6, and use the margin command on G times D3. And what do I have here? So I have 49.2 degrees of phase margin. I almost got it with the going for 55 degrees of phase margin. So maybe I needed to go for a little bit more. Maybe instead of 10%, maybe 12% or something. But let's say that this is close enough for what we're trying to do. And now what I'm going to do is say that we have G closed loop. What different designs do we have here? Oh, let's do the first one. So I'll call it G closed loop 1, and that would be G times D1 with unity feedback. Whoops. Doesn't make sense, does it? Equals feedback. There we go. And GCL3 is this last one that we did. All right. Now, we could do a lot of different things with this, but let's make a step response of these two. So I'm just going to compare these two designs. Now, admittedly, they don't quite both meet all the requirements, right? So GCL1, the phase margin wasn't quite right, but we can make a step responses of these. And this is what you get. It's pretty classic lag compensator step response. And that is that it has this long-winded tail on it, like so. So that means that things like, if you do a step info on this, GCL3, which was pretty close to meeting the design requirements, 50 degrees of phase margin, has something like a settling time of 8.3 seconds. I mean, that thing is slow. It's got a little bit of overshoot, It is what it is, but it's a slow response in general. Now, let's do a final design. We could actually take the design we have for this one, and all we need to do, we could ask for more phase, or we could take this thing and maybe throw a 20 up there. So I'm just going to move that phase bubble a little bit further to the left. And I'm pretty much done at that point. So I'm going to call this D4 now. And if we do a margin, I guess I should make a new figure. Margin on G times D4. 52.1. How do you like that? So I guess we'll call that one pretty much cooked. We have a little bit extra phase margin. That's okay. It's going to be a rather slow, sluggish response, but we won't need much actuator effort out of it. And as a parting shot at this, let's estimate the closed loop bandwidth. Here's our gain frequency of the compensated system. It's at 1.76 radians per second. So I will hazard to guess that the closed loop bandwidth is somewhere between 1.8 and 3.5 radians per second. So let's check it out. I'm going to say GCL4 is equal to feedback G times D4. And we'll make yet another plot and go Bode. I love the Bode word. It's just kind of a cool word. And there it is. Classic. Let's throw a grid on it. Whoops. Yep, that's what I meant. A classic closed loop Bode plot. Low frequency, we're at 1 or 0 dB, 1. Tracking that sine wave just nicely, very little phase loss, and then we start rolling off some phase. We've got a little bit of a bump here, and then down it goes. Getting almost nothing out of it at that point. So let's find the 3 dB down point. Oh, where is it? Oh, there it is. 3.7. Oh, what am I doing? I got the wrong thing. Okay, so. Oh my gosh. There it is. That's close enough. So I'm down 3 dB, and the frequency is 2.9 radians per second. Ta-da! 1.76 to 3.52. Okay, so we are going to make I'm going to clear out my Simulink data inspector, and we'll fire up Simulink blank model. What we'll do is make a quick little simulation of this. So I'm going to go transfer function. Oh no, I didn't get it. That's what happens if I hit the thing too fast. There we go. Okay, and in here I'm going to put g.numerator and g.denominator. And we'll put our controller in there. And that was D4. for let's add up some signals. And what we're going to do is hit this thing with a little bit of a sine wave and look at our closed loop frequency response, sort of like line by line, and see if it compares well with our Bode plot. Okay, so this is out, this is in, oops. Oh, what's that? Huh. Okay, and I'm going to go modeling, settings. I'm going to pick a time step for this. The time step needs to be commensurate with the plant. Well, everything, but the plant is probably the fastest thing that we have in here. I'm going to go to 10,000 seconds because we're going to do a really slow sine wave. And I'll use RK3 or ODE3 and a time step of 0.02. That should be more than enough to get our 2.5 pole sorted out. Make that bigger for you. All right, so let's look at our closed loop Bode plot. 0.1. What did I have this set to? Oh, I didn't set it to anything. Let's set it to 0.01 radians per second, which is this point in the Bode plot, right? 0.01, and the magnitude has no attenuation essentially, and the phase is pretty good. So when we run this, and then look at it in the Simulink Data Inspector, we should see pretty much a really nice match between the input and output. There's the sine wave, and there's the output of the controlled system. Obviously pretty good. So now let's go to let's look at the Bode plot. Let's go to, how about 1 radian per second right here. So the magnitude should be a little bit higher actually than what the output magnitude should be a little bit higher than the input, and there should be a fair amount of phase shift, like 30 degrees or so. So we'll say 1. We can knock this down to maybe 100 seconds because each sine wave is going to take about 6 seconds to go. Check that out. So let's go to another point on the Bode plot. How about our 3 dB down point, which is at 2.87 radians per second. And what we should expect to see is the magnitude attenuated by 0.7. And I can decrease this a fair amount. 2.87, so if I go 2.87 divided by 2 divided by pi, 1 over that, there's the period for 1 sine wave. So I'm just going to go like 50 seconds and run that. And here we go. So the blue, again, is the input, and the red is the output. And we can see it's attenuating, and we have this crazy phase shift. Let's throw a cursor on there and check it out. 0.7. 0.706. So 3 dB down is actually 1 over the square root of 2 in terms of attenuation. So that would be 0.707. So this is really close. Matches with, theory, if you will. And as I keep going up in frequency, if I were to go up to, let's say, 30 hertz or 30 radians per second, just run this for 5 seconds. Run this, and it's funky. There we go. And oh, why did I go to 505? How about 5 seconds? And now my time step is too coarse, and so let's back up a second. I picked that time step based on the dynamics of this plant, ignoring the input because the input was really slow. But now the input's kind of fast. My time step is fine for this, but it can't really resolve this fast input. So I'm going to tighten up my time step a little bit so that the response that we're looking at isn't all jagged, and run that little stinker, and there we go. So the input is the blue, 1, amplitude of 1, and the output is the red, and it pretty much isn't responding. This is classic of every physical system. If you shake it fast enough, it doesn't respond anymore. That's it. Enjoy. Hopefully this helps with your lag compensator skills. Bye-bye.